Hey everyone, it is December 17th, 2019. Time's about 14:25 CST. It's 34 degrees Fahrenheit out, and it is Geo-Rant time number 116. This is another one of my Geo-Rants that will go into that are applicable to the geo-files episode that has not been released yet. It will be linked below, and this will be linked in the geo-files episode. But I'm going to go over Nicholas Steno, the Danish guy who lived in the 17th century, 1638 to 1686, who developed 4 laws of stratigraphy, or back then principles. And they were, I'm not going to lie to you, at the time, based off assumption. Yeah. But, as I've already shown you with radiometric dating, we have a check on Steno's laws. They do confirm one another. They validate one another. And another way we can confirm Steno's laws is by using his laws to extrapolate units into the subsurface. And we do that. Those are called cross-sections. I showed you one of those before. Those mesh up. So we have 2 things that support Steno's basic laws. But there is a misconception about Steno's laws, especially among young Earth creationists. The more I interact with them, the more I'm pushed to believe that they think Steno's laws should apply globally from one outcrop to another with no breaks or anything like that. Now, to be a law, it has to apply universally, but it doesn't have to apply to the whole of the planet simultaneously. And I can tell when young Earth creationists are trying, some do try to understand, there's some that don't care, but when they come in saying things like geologic column, isochronous layers, these are not terms geologists readily use. I don't want to say we never use them, but we rarely use them. As a matter of fact, isochronous layers are really used for glacial stuff. They're not used for standard stratigraphic models. We don't use that term. And I've already gone over how we don't use geologic column. And if I hear you say things like erosion marks, I know immediately you're totally full of it, because that is strictly a young Earth creationist term that Eric Hovind pulled out of his backside when he was recording Scarred Earth. No geologist says that. All right, but anyway. So, Steno's laws, I'm going to explain them to you the best that I can. Now, remember, when you are out in the field making a geologic map, usually the ones in the Midwest are at the 1 to 2400 scale. That's a quadrangle. So you're mapping an area a little larger than a township. All right, township's 6 miles by 6 miles. These are bigger than that, but it's still a small area. So you're going to develop your stratigraphic column, which I showed you before. Here, when you make your maps, you're going to develop one of these. All right, and oh, my train of thought just derailed. So you're going to make one of those, but when you make your map, you're doing a small scope. All right, so essentially, Steno's laws are going to totally apply where you are. Now, take something like the Illinois Basin, for example, or the East Interior Basin. They're the same thing if you see them in the literature, all right? The Illinois Basin, if you go out in Illinois and go to, say, the top of the Silurian Sugar Run Formation, you take strike and dip, you are not going to get anything steeper than a degree, if you can even measure that, all right? That's essentially level. All right, it was deposited levelly. But if you take the Illinois Basin, zoom out to the size of Illinois and Southwest Indiana, and take the Illinois Basin and vertically exaggerate it, you're going to see that the units were deposited like this. They're thicker towards the middle of the basin. They're thinner at the edges, which is exactly what you would expect if sediment was being shed from the edges towards the center. But in order to do that, you have to zoom out to a regional scale and extrapolate it, all right? Now, that's assuming there's nothing there to interfere with that basin's sedimentation. No tectonic activity, no orogenies, no faulting, no intrusions, and of course that never, ever, ever happens. But I just wanted to explain to you how Nicholas Steno's laws are universal but only in the area you're working with at the time. You cannot, you can use the laws anywhere you're working, okay? That doesn't matter. But you can't take a stratigraphic column from here, a stratigraphic column from here, a stratigraphic column from here that are separated by thousands of miles and just draw lines to connect them because you think all those units correlate. That's not how that works, all right? But so let me get into them here. First of all, here they are. The 4 basic principles or laws of stratigraphy. Okay, you can see there, number 1, law of superposition. 2, the law of original horizontality. 3, the law of cross-cutting relationships. And 4, the law of lateral continuity. And you can see I had diagrams under here, and I whited them out because I decided to make cards for you instead. I'm going to go through these with you. Okay. The law of superposition. Now, there's something you need to understand here. These laws technically only apply to clastic sedimentary and chemical sedimentary rocks of marine origin. This does not apply to transition zones like deltas, and it does not apply to terrestrial deposits, okay? They apply to marine sequences, all right? And sometimes, on occasion, igneous surficial lava flows apply to these laws as well, all right? So here, all right? Basically, the law of superposition only applies, like I said, in undisturbed surface deposits. In marine basins, younger deposits are above older ones, all right? Oh, that was cross-section 2. Sorry. So a basic textbook example of the law of superposition, we're going to come back to this for law of original horizontality, basically states that in an undisturbed sequence of sedimentary rocks that were deposited on the surface, that does not deal with intrusions, this here, oldest to youngest, our yellow is our oldest, and our brown is our youngest. So that was deposited first, deposited second, deposited third, deposited fourth. Okay. Now I'll get to cross-section 2, which I inadvertently showed you. All right. Okay. Superposition. Does this conform to the law of superposition? No, it does not. It is not an undisturbed sequence. I cannot, if I were to draw a well, say here, I'm going to get a totally different stratigraphic column than if I did one here, if I did one here, and here I might get the same ones I got here, but I get different depths. So if I had an outcrop here, 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 and here, they're not going to look exactly the same. Why? Because we have stuff going on here. We have faults. We have an igneous intrusion, a dike that breaks off into sills. The fault caused deformation, an anticline, a syncline, an anticline, a syncline. What's with this up here? Well, this here is an angular unconformity. There's erosional in origin. And what are these striped lines? Those are crossbeds. I often hear young earth creationists allude to a Colorado experiment which shows layers being propagated at the front of the previous layer. Yeah. That's delta propagation. This is news only to young earth creationists. It's not news to geologists. We know about crossbeds. There are dozens of types of crossbeds, all right? This is not news to any of us, okay? And they don't, and if you, like, a delta starts propagating, it's going to deposit a bed kind of like this, another one on top of that. That does not violate necessarily the law of superposition, because up, in that case, isn't here. It's this way, okay? It's up based off your deposition. It's not up based off the center of the earth to the sky, because if it was, we would have to use that for things like this as well. And Earth is a very dynamic planet. Things are not simple, okay? Now, we're going to go to the law of original horizontality. And I saw this for cross-section 1. We can use this again. That basically states that sedimentary layers in a marine sequence and superficial sedimentary layers with superficial lava flows can be included in that, will deposit nearly level with zero dip or really close to it. And like I've already discussed, on a small localized scale, that is very true. Right? But if you're in a basin or something like that, or on a dome, obviously things change. Okay, and I already went in that, and I'm not going to go into that again. So still, law of original horizontality, you know, level, 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 pretty level. Obviously there's some, you know, there's some dip, but essentially level. Okay. And an exception to this, which I'm going to show you, and I actually modeled this off of Baraboo, the North Limb, if for any of you have seen that video. Law of original horizontality, cross section 2. Here's exceptions to this. Remember how I said marine sequences? This is not a marine sequence. This, see these squiggles? Those are ripple marks. These are beds. Notice how they are turned vertical. You cannot deposit ripple marks on a vertical wall. That means this geologic unit, analogous to Baraboo quartzite, has been tilted vertically. It was deposited like this, not violating any laws, but the earth moves. We have things like orogenies, and it was deformed, turned vertical. At the time, these would have stood as hills as erosion took place. Then seas came in this way. But before they did that, we have sand dunes and crossbeds here. This would be that Aeolian facies of the Galesville that I've shown you before. So this is also not a marine deposit. But sea level continued to rise, and we get a marine sand. And say it has burrows in it, and I've showed you at Baraboo, I showed you a rock that does have burrows. So that's how we know it's marine. And you see right up against the quartzite, you get an initial dip, but it levels out from there. These are alluvial fans. These are also not marine deposits. What would have happened is you had a minor regression, and so you could have talus pile up, and alluvial fans do have initial dip to them. This is also no secret. Okay, this is only earth-shattering to young earth creationists. All right, this is not new news. The whole, I mean, I've shown you guys my textbooks before. This is not simple stuff, all right? So let's go to cross-cutting relationships. This one I will be using for cross-cutting relationships and lateral continuity, okay? So cross-section 1. What we have here is we have our basement rock, and we have a lava 1, a lava 2, a lava 3, and a conglomerate here, a sandstone here, and a dike here. Those of you who know me know I love the Mid-Continent Rift in Lake Superior. This is kind of modeled after that area. Our basement rock here, all right, it exists. It's obviously been weathered. It has cracks in it. This lava 1 gets deposited on top, okay? And it does have some initial dip right here, but generally this is level. And now this would be a superficial deposit. Cross-cutting relationships and lateral continuity apply not only to marine sedimentation. They apply to the rocks in general. All right. The first two are restricted to more or less marine sediments. These are not. All right. So our first lava comes in. Then there's an unconformity, obviously, on top of the lava because we had time to weather out a conglomerate. Another lava comes in on top of it. More time passes. See, this is a high area, so we get a pinching out. We get a sandstone on top, this yellow, but it pinches out towards the high ground. Geologic units can pinch in and out. They can thin and thicken. This happens in the Mid-Continental Rift all the time. Look at the old geologic maps from the 1950s of the Keweenaw Peninsula. You'll see this in action. Look at my maps. You'll see it. All right? This doesn't continue forever, okay? So there's nothing wrong there. Like I said, this is not news to anybody, okay? Lava 3 on top of the sand, and then this dike comes and intrudes everything. So what's that mean? That means, and I'll get into these red dates here in a minute, but that means our basement was first, weathered, we have an unconformity. Our lava 1 was deposited. That's our second unit. Basement is our oldest, and we know that from several lines of field. We have field evidence. We have a big zone on top of our basement, and we also have xenocrysts of the basement at the base of the lava. Our third confirmation came from the date. Okay, so, oh, I forgot to put a date on the basement. We'll say it's 2 billion. We'll say it's a 2 billion year old granite. Okay, sorry, I forgot to do that, my bad. Okay, so those all line up with one another, okay? And so then our conglomerate came, then our lava 2, then our sandstone, then our lava 3, then our dike, because our dike cross-cuts everything. It has to be the last thing that formed because it intrudes everything. You cannot intrude if these rocks don't exist, okay? So this has to be the youngest, okay? Using cross-cutting relationships, that's the youngest unit. And as you can see, we have dates here. Now, they do overlap a little, which can happen if you're dating thin lava units really related to one another, because they can pick things up from underneath, all right? But it doesn't violate any law of stratigraphy. These all jive with one another. The law of cross-cutting relationships is fine, okay? So let's get into our last one, law of lateral continuity. Okay, let's take this again real quick. This one's hard to describe and explain. Basically, I'm going to read this. Lateral continuity. Layers of rock are continuous until they hit an obstruction. Obstructions would be things like faults, intrusions, or they just pinch out. Okay, here we have obstructions. But is this conglomerate a different conglomerate than this? Is this sandstone a different sandstone? Are these lavas different? No, they are not. Because using our law of cross-cutting relationships, this dike didn't exist when any of this was deposited, okay? So we can still use lateral continuity across it. If we just had up to here, that might be a different story, okay? But we don't. We have the whole thing. So we can still use the law of lateral continuity across a single dike, all right? Now, a better illustration of that, a more detailed illustration of that would be this. Okay, now we have an obstruction here. We have a normal fault, up, down. This is our topographic profile to scale. This is we'll say this is a canyon. Doesn't have to be the Grand Canyon, but you can think of it that way if you want. We have these geomorphologic structures here. And then you have your deep valley here. We'll say there's a little stream at the bottom. Okay, so what is lateral continuity? All right, see how I have blue here, green here, yellow here, orange here, brown here, and this little red knob, all right? Lateral continuity states, this blue is obviously one unit. We can even get in the bottom of the canyon to see. There's no, even though it's been eroded up here, it connects down here, okay? So that is one unit. Is the green the same unit? Yes, that's what these red dashed lines are. The law of lateral continuity says we can extrapolate across. Now we get to the top here. This little red knob, he's an erosional remnant. Let's say outside of this cross section, there's a bigger, exposure of it. So we just extrapolate the best we can, all right? I mean, it's quite possible this red dashed line comes up right like this and meets with the fault up here, about right here. But, err on the side of caution, we'll just extrapolate right there. Here, we have a facies change. The yellow, we can lateral continuity says we can connect the two across the valley and across this smaller valley with the orange. Now, is the orange the same geologic formation as the yellow? It may or may not be. See, the thing with lithostratigraphy and designating formations and formal units, it has to do with the physical characteristics of the rock. But how we divide it has to do with other things. If there's no economic reason to divide these two, this orange and yellow, and they are only local, they might be one formation. If this gets thicker this way, this gets thicker this way, they might be designated as two formations, and there could be a vertical cutoff like over here or something. Okay? So that's that stratigraphy is our way of talking about the interior of the Earth. But for lateral continuity purposes, see, this grades into another rock. That happens all the time, even in marine sequences. But if you look at the bottom and the top, that means that right there shows us that using the other laws, that the yellow, the base of the yellow here is the same age as the base of the orange here. They're just not lithostratigraphically correlative. Okay, they're not the same lithostratigraphic unit. Oh, I hope that was clear. One more thing I'm going to go over before this becomes an hour. Remember how I showed you the strat column in Geo-Rant 115? I forgot to mention, why would I draw it like this? Why would the slate be recessed? Why would the dolostone be sticking out, the sandstone and basalt sticking out, and the gabbro like this? Because when we draw something like this, this is a weathering profile on this side. Because a lot of times, topography can clue us into this geology, especially if it's not exposed. So you've got, like over here, I got a bunch of forest and trees and grass over here that could be covering something. I can use topography to infer. That's what this does. That shows me the slate will weather out before the basalt or the dolostone will. So that's where this comes in. All right. See, we got a pullback here. This yellow unit is weathering out before the green. Okay. And see this weird jagged pattern? We wouldn't put that on our stratigraphic column unless it was the very top unit. We might do that, but we would definitely stick it out. So this would be our yellow on this, and this would be like our brown. Okay. Anyway, that's it. I hope I explained that thoroughly. If you have any questions or comments, please leave them below, and I hope you learned something.